Hello, today I'll be introducing our paper Model-Based Uncertainty in Value Functions to be presented at this year's AI Stats. We tackle the reinforcement learning problem where there is an agent that interacts sequentially with the environment. The agent issues actions and the environment returns observations and rewards. The goal is to find an action selection policy that maximizes expected cumulative rewards. For real-world applications, we need to be efficient and limit the amount of interactions with the environment required to train a good policy. For that, we consider the model-based reinforcement learning setting, where we additionally train a generative model of the environment that allows us to collect more data and model uncertainty. Now onto some preliminaries. The Bellman equation is a recursion that converges to the expected sum of rewards, also known as values. We can think of it as a black box function whose inputs are environment dynamics, modeled as a Markov decision process, and the policy, and whose output is the scalar value function. In the model-based setting, we can plug in our learned environment model that has uncertainty in the dynamics due to finite amount of data coming from the true environment. This type of uncertainty is often called epistemic uncertainty and is useful for exploration as it identifies regions in the state space with low data density. Interestingly, this uncertainty is also propagated through the Bellman equation, resulting in a distribution of values. And as we gather more data, our epistemic uncertainty shrinks and the distribution concentrates around the true value function. In this paper, we ask ourselves how can we estimate the variance of such a distribution of values with the purpose of using this variance as a signal to efficiently explore the environment. Prior work has proposed the uncertainty Bellman equation as a recursion to estimate the variance around values. Similar to the standard Bellman equation, it receives as an input what we call an uncertainty MDP, which has its own notion of local uncertainty rewards and uses the posterior mean dynamics from our learned model. Given a policy, the key idea is that the uncertainty is propagated over time and the UBE converges to some estimate of the variance of the value function. Prior work proved that under some assumptions about the MDP and given some definition of uncertainty rewards, the UBE converges to a guaranteed upper bound on the variance of values. Follow-up work redefined the uncertainty rewards and obtained a tighter upper bound, but still, overestimation can lead to inefficient exploration, as the agent will have to gather more data to resolve the uncertainty. The key question we asked ourselves is whether we can close the gap further and obtain sharper variance estimates. We answered this positively in the paper. First, under the same assumptions as prior work, we define new uncertainty rewards such that the UBE converges exactly to the variance of values. Second, we explicitly characterize the gap in previous work and show that our uncertainty rewards close the gap by accounting for aleatoric noise coming from the stochasticity of the dynamics and the policy. In the paper, we propose a practical algorithm to estimate the solution to the UBE in both tabular and deep RL problems. Regarding the environment model, in tabular problems, we use analytical posterior updates starting from a Dirichlet prior for the dynamics. In deep RL, we use ensembles of neural networks to represent the distribution over dynamics. To estimate the uncertainty rewards, we require samples from the value distribution. In the tabular setting, we can directly sample MDPs from our posterior distribution and solve the corresponding Bellman equation for each sample. In deep RL, for each member of the ensemble of dynamics models, we train a Q function on data generated by the corresponding model. Lastly, to solve the UBE, in the tabular problem we can solve the UBE exactly using the approximated uncertainty rewards. In deep RL, the UBE is modeled with a neural network whose output layer is a soft plus function forcing the output to be positive and thus interpreted as a variance. This network is then trained via TD learning using standard techniques. We incorporate our variance estimates into policy optimization using the principle of optimism in the face of uncertainty. In short, the policy is updated by taking the argmax of optimistic values, defined as the mean values, plus some factor lambda times the standard deviation of the values, where the variance estimate is precisely the fixed point solution of the UBE. Now let's have a look at how the algorithm is able to tackle difficult exploration problems. First, we consider a standard exploration benchmark in tabular RL called DeepC. The agent starts in the top left corner, and every time step must decide whether to move left or right, while always dropping down one level. Moving right has a small cost, and the only positive reward lies at the bottom right corner of the map. The agent must select to go right at every time step in order to observe the sparse reward. As such, the problem becomes exponentially difficult with the size of the environment. In this video, we will observe how our optimistic agent solves this problem efficiently when equipped with the UBE variance estimate. On the left, we observe the visitation counts, and in red, the trajectory followed by the agent at every episode. On the middle plot, we observe the standard deviation of values estimated by the UBE, and on the right plot the predicted value of the policy. At first, we have large uncertainty across the board, but it quickly gets resolved as the agent starts exploring the environment. Uncertainty remains large in unvisited states, pushing the agents to visit them. Note how the value function will remain close to zero until we actually observe the sparse reward. Once the reward is observed, the value function will encourage the agent to constantly visit the diagonal states. Since there is a sampling process involved in estimating uncertainty rewards, the agent will still visit occasionally off-diagonal states to resolve the remaining uncertainty. Now we'll have a look at how the agent solves a pendulum swing-up task with sparse rewards. The pendulum is always initialized in the downwards position, and we must apply a torque sequence that swings the pendulum until it reaches the upright position. The only positive rewards are close to the upright position, and additionally, we add a small penalty proportional to the applied torque. Agents with naive exploration strategies will often converge to the suboptimal solution of not applying any torque at all. In the left plot, we have the mean value function predicted by our agent, where the x-axis is the angle of the pendulum and the y-axis is its angular velocity. The sparse reward is found in the center of the square, with angles and velocities close to zero. Similarly, the right plot shows the output of the neural network modeling the variance estimates. As time goes by, we can observe that some structure starts to appear on both networks, and the uncertainty becomes large in regions of interest, for example, where there are sparse rewards and then in the border of feasible swing-up trajectories. At this point, the agent has found a close to optimal solution, and the uncertainty is generally low. To conclude, we found new uncertainty rewards that close the gap in estimation of the variance of values. We estimate this variance of values by solving an uncertainty Bellman equation. Then we use these estimates for optimistic policy optimization. And lastly, we found good empirical performance in difficult exploration problems. Thank you for your attention, and if you want further details about the paper or our implementation, you can scan these QR codes, or you can also check the links in the description.